Trees. Definition. A tree is a connected graph having no cycles. A second definition. A graph containing no cycles is called a forest. Now look at the difference in those two definitions. A connected graph with no cycles is a tree, but any graph with no cycles is called a forest. So a forest can have disconnected pieces. For example, below we have a forest of 3 trees. There's 3 disconnected pieces or 3 connected graphs there. Each one of them is a tree, and we can have one or more trees together in one graph that are disconnected, and that becomes a forest. In a tree, a vertex of degree 1 is called a leaf. We have, as you see, in the first one, all but one vertex is a leaf because each of them is of degree 1. The one that kind of looks like a real tree has lots of leaves up and around the upper portion where it's degree 1, but notice many of the other vertices have degree 4 or degree 3 or degree 2. And in the last graph, the 8 vertices along the bottom of the graph are all leaves. A spanning tree T of a connected graph G is a spanning subgraph of G that is a tree, that is, V of T is equal to V of G. The number of vertices in the tree is equivalent to the number of vertices in the graph. Well, for example, look at this graph G that has 5 vertices. This is not a tree because there are many cycles, such as A, C, D, A. But if we look at T, notice we have the same 5 vertices, A, B, C, D, E. This time there are no cycles. So since there is no cycles and it's connected, T is a tree, and that tree spans graph G, meaning it has all the same vertices as graph G. And there are probably more than one different spanning tree of graph G. This is just an example of one of them. Theorem. Every tree of order n has size n minus 1. So the size is 1 less than the order. And for example, recall that the order of a graph is the number of vertices, and the size of the graph is the number of edges. Looking at one of our examples from earlier in this video, this graph is a tree. If we count the vertices starting at the top and going down, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 vertices. And if we count the number of edges starting at the top, in the top, what I'll call a row is 2, and then in the middle row, there are 4, 2 and 4 are 6, and across the last row, there are 8. 8 and 6 are 14. So this tree is of order 15 and size 14. That is, it has 15 vertices and 14 edges. And conversely, and by that I mean that if we take the first theorem at the top of the page and rewrite that in if-then form, and then take its converse. There is another theorem that has been proven by mathematicians. Every connected graph of order n and size n minus 1 is a tree, meaning it can have no cycles.